the question is, can we do the same thing in global simulation? In a global simulation. So we want to solve the dynamics of the whole star. So there is two ways to do that. A spherical harmonic code or a star-in-a-box code. And now with spherical coordinate, we can do that also with spherical coordinate. So there is the plus and minus for each method. The plus, the good thing for spherical harmonics code is that the sphere is the external sphere is the surface of coordinate. It means that it's very easy to specify the boundary condition at the top. The sphere is corresponds to R equals something. And the precision of the code is spectral, because sometimes it's a Chebyshev grid for the radial part and the Legendre polynomial for the angular part. So the precision is spectral. The big problem with these methods, the center is the singularity. The center of the domain remains the singularity. Not the axis, because the spherical harmonics are normal function for the axis. The basis is regular, but the center remains singular. Also, the nonlinear terms are quite difficult to compute because they should be computed in the physical space. So if we did in that code, all quantities are developed on spectral basis, and then we want to compute v grad something, we have to come back in the physical space, compute the nonlinear term, and go back to the spectral space. So there's a lot of back and return transformation between spectral and physical space, and that's quite easy to compute.
That's what is called a pseudo-spectral code, technically.
Yes, pseudo-spectral code, yes. And also, the parameterization is non-trivial in this, because, for example, the one way to use parameterization is to make transposition. It means that, for example, if we want to compute the derivative in the radial direction, for example, and your code is parallelized on the radial direction, that's okay. But if you want to derive something on the theta direction, that can be a problem. So some people are doing that by transposition. They put all the theta direction in the first rank of the array, where there is parameterization, compute the derivative and go back. So that's quite hard also to do. So the star-in-a-box simulation, the center in this case is no problem. It's not a particular point of the grid. It's highly parameterizable, the scalability is linear, and the nonlinear terms, of course there is no problem because we remain in the physical space all the time. But the problem is first that half of the grid points are lost. All the points which are outside the star are lost. We compute that point, but we don't need that point. Another thing is that it's a non-spectral precision. Of course, we don't use spectral basis, and then we have in the best case we have the spectral the precision of the machine. And in this case, we are non-conservative, not really the precision of the machine. And maybe the most problematic thing is that boundary conditions are quite problematic in this case because the sphere is not the surface of coordinate. So we have to be careful about it. So what we try to do, as in the S-lab geometry, we deal with polytropic layer, superposed polytropic layer. That's what I coded last year. So it's a convection zone below above a radiative zone. And at the top, we apply a cooling zone. And this cooling zone is very important because this cooling zone imposes the sphericity of the star. Because the cooling term is a radial one. Okay? And the problem is that we want to force the convection, we have to have some heating term at the center. And the heating term is inspired from the Wolfgang and Sticks and Brandenburg paper in 2006. Except that now we are in 2D, not in 3D. So the heating profile, which is a nuclear, something like nuclear region at the center, in 2D it's this form for a Gaussian profile. And for example, the radiative equilibrium imposes this one, and then the flux is simply given by the integral of this profile. And in this case, everything is analytic. That's a good thing. So the luminosity is given by this one, okay? And the flux is given by the luminosity divided by 2 pi r in 2D, and not 4 pi r squared. Okay? And the flux is related to the temperature gradient. So you see that the temperature gradient is analytic in this case.
Why are you doing a 2D thing now? In the star in a box, why are you sticking to 2D?
For the moment it's 2D.
3D will be costly.
And then, but that's for radiative equilibrium. So we have also to take into account the hydrostatic equilibrium. And the hydrostatic equilibrium for polytropic setup means that the gravity field is related to the temperature gradient. And then the gravity field now is also analytic, is related to the luminosity profile. And then in the code that's quite difficult to manage because the gravity field in the spherical setup is actually is there in the gravity underscore r subroutine. But in my case, all of these parameters are introduced in the entropy module. And then actually I'm dealing with this analytic profile using the FRA stuff. But I define gravity field in the entropy module. So that's quite strange, but the gravity field in my case is FRA defined in entropy module, not in the gravity one. And then, for example, I'll show you a setup using a polytrope m equal to 0 as in the convection zone, and the radiative zone with polytrope index m equal to 5. And maybe you know that the critical index, polytropic index, is 3/2. Okay? It means that if the polytropic index is larger than 3/2, we have radiation, and if it's below 3/2, we have convection. Okay. And then I show you a typical Gaussian heating profile here, the corresponding luminosity function, okay, and the corresponding gravity field. Okay. So everything is analytic in this case. So that's what we obtain in this case. So at the top, it's a cooling zone. So the cooling zone imports the sphericity of the star. And here, we heat the star. And then what you see, we obtain exactly the same topology of in the S-cloud. It means downward plumes. And the plumes normally should stop here, which is the bottom of the convection zone. And you see that the plume penetrates in the radiative zone. So actually, we are working on that, especially on the post-processing of that, which is not very evident. For example,
So when it comes to the bottom, it just spreads out like a mushroom?
Yes, when they come to the bottom, you see, for example, this blue thing, she's tilted. And she's tilted because of internal waves. The internal wave propagate mainly horizontally. Okay? And then they knock the plumes. You see?
And also it looks like mushrooms then.
Yes,
Mushrooms.
exactly, like a mushroom, yeah. But you know in geophysics, the mushrooms are in the opposite direction. Plumes, when you compute convection with an infinite prime number in the mantle of the Earth, you find plumes in the other direction, like that.
So this is undershoot, not overshoot.
What?
So this is really undershoot, not overshoot.
And then you see, for example, what I'm doing actually, I can show you in reality. The problem is to the post-processing in this case. So I wrote some routine, ideal routine to take into account the spherical setup. So for example, here I compute, I call this one SPH_flux, which computes the convective flux, the radiative flux, and the kinetic flux. But the problem is that the fields are known on the Cartesian grid, and we have to recover the field on the radial grid, and also angular grid. So to do that, there is two ways. First way is interpolation. So we define a new grid, a radial grid that we know the point, and we interpolate the field on this point. That's one way to do that. The other way to do that is to, as Wolfgang did in the past, is to progress using a radial filter. For example, I want the mean, the radial mean of, not the radial, the angular mean, for example, of any quantities. And then it's something like a filter here, a radial filter, so over down, like that. It means that we take all value of the field which are included in some spherical shell. Okay? And the width, the filter is something like that. It's a Gaussian profile. And then we advance this profile between 0 and the 0 and we advance this width function until the surface. And at each time we sum all value which are on this spherical shell. So that's another way to do. And the two methods give exactly the same result. The interpolation one and this one. So for example, I'll show you here, so that's very important to conserve the flux in this simulation. So here you see so maybe it's not very clear. In the solid line are the radiative flux. Okay. So now we have to forget the constant radiative flux in the radiative zone because it's a luminosity function. So the flux is not imposed at the bottom. So the radiative flux here, so in the bottom of in the radiative zone here, the flux is controlled by radiation, and then the radiative flux go down in the convective zone because the convective flux go up here. It's a dotted line. And you see here the convective flux is not 0 at the bottom of the convection zone. So it means that we still have penetration. Becomes negative and go to 0. Okay? And here this line is the total flux. Not very clear. And the dotted line here is the theoretical flux given by the luminosity function divided by 2 pi r. So we see that the total flux behaves exactly as the theoretical ones. Where this one. This one is the total flux, and the solid line, which is not here, this one is the total flux of the simulation. Okay? This one is the theoretical one.
4 pi squared, you mean, not 2 pi r?
No, because we are in 2D.
2D, yeah, sorry.
And that's one thing I forgot at the beginning. Shit, I don't recover my luminosity function.
Yeah.
And then I realized that the setup was false. And now if you look at the entropy module,
Yes.
you realize that now we have 3D and 2D case for
Yes.
the luminosity function.
Right.
Yes. So that's actually what we are doing with the star-in-the-box simulation of field particulation. So now I will show you. I would like to
m equals 4 for the time, yeah? Is that true?
m equal 4. No, in this case, m equal 5, m equal to 0 here. So that's radiative zone.
Did you stop the movie at some point?
Hmm?
You stopped the movie at some point? Ah, yeah, it's lost the symmetry.
You can see the value of the polytropic index on the snapshot?
No. I was saying.
Yeah, it's the usual wave number.
No, that's an equatorial plane in this case. Huh? And the convective instability is not, is largely super. The real number is 25 here in this case.
Yeah.
impossible to find even. So now just 20 minutes on what we are doing actually with on the pencil code with my PhD student. It's called Thomas Gasti. Good guy, to be cool. And me. And then the problem is his PhD concerns the excitation of radial acoustic mode by kappa mechanism and the coupling with convection. Different. So the astrophysical context is the state-field instability strip. So you know that in the this is the Asher diagram, and you know that in the Asher diagram there is an instability strip which is called the state-field one, which means that any star which is in this strip normally is unstable for radial oscillation, and that oscillation are acoustic oscillation. And in this strip, the stars are giant stars. Okay? And this strip is very well known, except the red border. And Cepheid stars are very important because they are used for calculating distance in the universe. And they are very important because we know the period luminosity relation, which means that if there is a linear relation between the period and the intrinsic absolute luminosity of the star. It means that if we know the period of oscillation, period of the radial mode, fundamental radial mode, we are able to find the absolute luminosity of the star. And if we know the absolute luminosity of the star, we know the distance, because we measure the apparent luminosity, and the relation between the two is the distance of the star. So that's very important to know if a star is a Cepheid star or not. If the star belongs to the Cepheid instability strip or not. And then the blue border of the strip is theoretically well known, because the blue border corresponds to stars with a large effective value of the surface. And in this case, the ionization zone, which are responsible of the excitation of the mode, are, for example, the first ionization zone is hydrogen 1. The temperature is around 10,000 degrees Kelvin. And then this ionization region is at the top of the star, at the surface. And then the mass which is involved in the oscillation is too low to maintain the oscillation. I will show you why later. So the blue border of the instability strip is simply some kind of geometrical limitation. The ionization zones are too near from the surface. Then the classical Cepheid is like that. The ionization zones are deeper in the star, and the mass which is involved here is sufficient to maintain the oscillation. I will show you why after. Please believe me. And then the red border corresponds to stars which are solar value of effective temperature. And in this case, the ionization zones are very deep. Okay? But the problem, normally it should work, but the problem in this case, there is convection at the top, at the surface. And the bad thing is that the turnover time of the convection becomes of the same order than the period of the mode. And then there is a strong coupling between the oscillation and the convection. And in this case, this coupling is very not well known from a theoretical point of view, because one needs, in this case, a time-dependent theory of the convection. So theory of convection is mixing length, classical theory, and then one needs time-dependent mixing length theory. So some people are doing that actually. But for example, the best model we have actually has 11 free parameters. So 11 free parameters, you can play with that, with 11 free parameters, and with some key squares test, find some minimum, space space parameter, and then you can adapt this red border to the observed one. But so what? You don't control anything. So in our case, we want to understand the coupling between convection and oscillation. So the question, what is the influence of the convection zone onto the growth rate of a mode when the convective turnover timescale becomes of same order than the mode period? So, as I say to you, the modes are excited by kappa mechanism. And the first guy who found that is Eddington in the last century. And that's certainly the most beautiful paper I never read. That in this paper, Eddington is writing at the same time he's thinking. And then say, okay, I want that. How can I have obtained that? And then he'll write. And that's beautiful. For example, he said that in order to convert heat of any kind into work, the star or some part of it must behave as an engine in the thermodynamical sense. That is to say, you must take in heat, then it is a higher temperature than the average, and give out heat at a lower temperature. Just the opposite to what usually happens in natural conditions. So then he said, okay, how can I obtain a motor, an engine in this case? Possibly during the pulsation variation of the transparency, which governs the flow of heat, might cause the engine to be filled in the required manner. So that's what is called after the Eddington valve mechanism. So this mechanism is simple. It means that when a layer of the star is compressed by a mode, normally the opacity of the layer decreases because the opacity follows Cramer law. Okay? And then the temperature increases, the opacity decreases. And then the layer becomes more transparent to radiation. And then the flux can leave more easily the layer, and then one gets an extra luminosity after the layer, at the dilatation of the layer. But suppose that the opacity increases, then the temperature increases, which is the case in the ionization zone. In this case, then the layer is compressed by a mode. Okay. The opacity increases, so some part of the radiative flux is blocked by the layer. And then the extra energy is stored in the ionization process. And then the layer dilated, okay, some extra energy is given to the medium, and then compared to the adiabatic dilatation, and then you can maintain an oscillation like that. Okay, the mode becomes unstable. So Eddington found that the opacity should play a role, and effectively in the Cepheid star, at the top of the star, there is a strong increase of the opacity due to the first ionization of hydrogen, and first also ionization of helium and secondary ionization of helium. And in this region, the opacity increases when the temperature increases. So that's this case. And then there is a coupling between the blocking of the radiative flux and the oscillation. So in our case, we cannot reproduce the whole stuff. That's impossible. So we developed a very simplified model. We want to keep the physics and leave all which are not interesting first. So in our case, we decided to put in a box with constant gravity a radiative profile of the conductivity like that. Constant and a hole and constant. A hole in radiative conductivity means a bump in opacity, because opacity is proportional to the inverse of the radiative conductivity. So here it's an opacity bump, and it's a hole in conductivity. So our definition of the radiative conductivity is quite strange because it involves two arc tangents. Because in this we want to find the more generic profile where the width of the profile is not related to the depth of the profile, as a Gaussian profile, for example. And then the best profile we found is something like a combination of arctangent profile. It means that the amplitude of the hole is not related to its width, mainly. And then the first work to do is to compute the linear stability analysis of that. So that's a general oscillation equation for density, velocity, and temperature. And in this case, the radiative flux, the perturbation of the radiative flux now involves the temperature perturbation plus the perturbation in the conductivity. Okay. That's the motor, the engine of the kata mechanism here. So the problem is first to compute the correct equilibrium of that. Because the equilibrium in this case is nonlinear. We have the hydrostatic equilibrium and we have this relative equilibrium where the conductivity depends on the temperature. So to do that, we use an algorithm which is called the fixed point algorithm. It means that we start from a given profile for pressure and temperature and density, and we iterate these two equations until we converge towards the solution of these two equations. Okay. So, for example, for 3 holes of conductivity, here is that, between 0 and 1, and for the 3 holes, we find here the temperature profile. Okay. So you see that it's not changing very large because, in fact, the only change are around the hole. Okay, around the hole, we see the temperature decrease here. Because a lower conductivity means higher temperature gradient, and then the temperature gradient becomes steeper. Okay. So that density and this quantity is very important for the kata mechanism, is a derivative, the vertical derivative of d log k divided by d log t. It means that how the relative conductivity behaves at temperature.